Hello, everyone. Thank you all very much indeed for coming. My talk this year is on parallel universes, the idea that there are not just our universe, but millions, perhaps an infinite number of other universes where there are alternative realities in some sense existing at the same time as our own universe now. And in the scientific world, this is referred to as the multiverse, which indicates that it's been given, it has some traction, that this idea is not now dismissed as a nonsense by the scientific community, but that it has some credibility. And this is what I want to explain in my talk. So the history of the idea of parallel universes actually goes back, I've been reading today, all the way back to the 3rd century, when the philosopher Chrysippus suggested that the world eternally expired and regenerated, effectively suggesting the existence of multiple universes across time. And in modern times, the concept first appears in the late 19th century between the physicists Boltzmann and Zermelo. And much more recently in fiction, the concept first appears in the 1960s with the DC comic Flash Gordon, in the Flash of Two Worlds, where Flash meets his doppelganger counterpart on an identical Earth. Now, of course, since then, there have been many references to parallel universes in popular culture. I've just looked at Wikipedia to note a few. So in film, for example, we find The Golden Compass, based on the book by Philip Pullman. Of course, it's also in Star Trek, and it's in wacky sounding films like Doctor Strange and the Multiverse of Madness and Spider-Man Across the Spider-Verse. But anyway, I'm not here to talk about popular culture, but rather the scientific idea that there might really be multiple universes. And it's still controversial, and I'll tell you, it's controversial to some, but it's gaining wider acceptance. So I'm going to split this talk into 3 parts. First of all, I'm going to talk until about 10 to 1, so there's time for at least 10 minutes of discussion. And the talk will be split in the following way. So in the first part, I'm going to describe why there is a need for a theory of everything. Theory of everything is a physical theory that describes all the forces of nature. And that theory doesn't yet exist in a mature form, but I will talk about that. In particular, superstring theory. And I'm also going to be discussing what's called fine-tuning in the universe, why the universe seems to be perfectly fine-tuned for the existence of life, and why these 2 ideas suggest multiverse, i.e. parallel universes, may actually exist. In the second part, I want to talk about the Big Bang theory that we have and how its problems are solved by an idea called inflation, a very powerful unifying idea that explains the bang in the Big Bang theory. And in the third part, I want to put these 2 things together to explain how the combination of inflation and superstring theory create the multiverse. Okay, let's get going. So first of all, why do we have a need for a theory of everything? In fact, what is a theory of everything? So you will no doubt be aware that the universe consists of stuff. There is matter in the universe. It is not empty. So we have planets like Saturn in the top left-hand corner, and galaxies like M101 in the bottom left-hand corner, star clusters such as the Pleiades in the top right-hand corner, and life, you and me. All of these things and everything that we know is composed at its lowest level of particles, of atoms, and the forces between those atoms. And this is incorporated into something physicists call the Standard Model, which emerged in the 1970s. And it's a mathematical framework for describing all the particles that have been discovered in nature. And these particles are discovered by physicists by using enormous facilities such as CERN, the Swiss-French border, and also the Large Hadron Collider, where particles, atoms, protons, electrons are smashed together at enormous speeds to try and reveal the inner workings of nature. And so this Standard Model, which I'm showing you here, is broadly speaking, I'm not going to go into too much detail, consists of fermions, which are spin half particles, but you don't need to worry about what that means. And they describe, these are the elementary fermions, the particles that don't consist of any other particles, so they're elementary. And in the top left, we find quarks. These are the up-down charged, charmed, strange top and bottom quarks. In the lower half, we have the electrons, the three generations of electrons and their neutrinos. These describe matter, the sort of normal matter that we think of. And in the right-hand side, we have what are called the bosons, and these are the force-carrying particles. So these particles move between fermions and describe the four forces of nature. In fact, the three of the four forces of nature. The forces of nature are fourfold. There are the electromagnetic force, which is represented by the magnet and the lightning bolt in the top right-hand corner. Strong nuclear force, which keeps protons and neutrons together in the center of a nucleus. And the weak nuclear force, which is shown by the radioactive symbol in the bottom right-hand corner, which is responsible for radioactivity. I should have said that the electromagnetic force is responsible for keeping atoms together, the attraction of electrons to the nucleus, and also atoms bound together within molecules, and so is fundamental to nature, and is the reason why, even though the nucleus is almost completely empty space, you are still, the atoms resist your motion, and you can sit on a chair comfortably. You don't slide through the chair. But I did say that the standard model only describes three of the four forces of nature, and the missing force is gravity. And gravity, of course, is the great sculptor of the universe. And Einstein taught us, he replaced the theory of Newton by teaching us that mass curves space-time. So the heavier mass, like the sun depicted here, curves space-time, represented by that distorted grid in green. And the Earth, shown here on the right-hand side, also distorts space-time, but has a smaller dip. And gravity is the motion of objects within this distorted space-time. And this cannot easily be incorporated into the standard model. The standard model only uses special relativity, but this is general relativity. Special relativity is a linear theory. General relativity is a non-linear theory, and the two cannot easily be combined. And when they try to be combined, physicists come with nonsense results. They get infinities in their equations which can't be removed by a process called renormalization, which is used for the other forces. So there is an idea which has gained much traction in the last few decades, and that is superstring theory. And superstring theory is one of the main contenders for a theory of everything that incorporates all the forces of nature, including gravity. So I want to describe briefly what superstring theory is, because it's important for the talk. The idea is that when we see particles and detect particles in particle accelerators, the particles are in reality filaments of strings with very, very high tension. These filaments are not solid, as it were, but they are the filaments of energy, and that is the proposal. And that these filaments of energy with tension vibrate, as illustrated in this slide. Now, these strings can either be open, as on the left-hand side. They are one-dimensional, but they can oscillate in an open way, or they can oscillate in a closed manner, as we see on the right-hand side. And in addition, they can have different modes, different harmonics. So you see here that the string is the animation is moving between the fundamental, which is one vibration, one oscillation on a string, either an open string or a closed string. I'll try and do that again. So it's one oscillation, two oscillations, three oscillations. So by incorporating these different modes, these different oscillations, string theory is able to predict all of the particles that are seen within the standard model. And in particular, it also produces the boson. So this is the gamma, this is the electromagnetic, this is the photon, and most importantly, this is the graviton. Now, what I meant to explain earlier was that in electromagnetism, The force-carrying particle is the photon, which we saw, the first particle that was highlighted. In the strong nuclear force, we have the W and Z. We have the gluons. And for the weak nuclear force, we have the W and Z bosons. But for gravity, which is missing from the standard model, we have gravitons, which is a hypothetical particle that causes gravitation. And this graviton naturally arises in string theory, where it is absent in the standard model. And that's one of the reasons why there's tremendous excitement about string theory. And so string theory is able to account for all the fermions and all the bosons of the standard model, plus the hypothetical graviton for gravitation. But there is a catch. There is always a catch. The string theory is only mathematically consistent if you have not 4 dimensions, but 10 dimensions. So this is very strange, and you might think that physics has become a bit unhinged by this proposal. But anyway, we'll pursue it. So we are familiar with 3 spatial dimensions: left, right, up, down, back and forth. And so the location of any object in space, as I'm sure you all know, can be described by these a value of each of these 3 coordinates. And then we have the 4th coordinate of time, which is not illustrated in this diagram. But I said that for string theory, we need 10 dimensions. So we need 1 of time and we need 9 of space, which is very odd, very odd sounding to those not used to it. It does have a precedent, though. In the early 20th century, long before superstring was formulated, but after general relativity was formulated, a mathematician called Oscar Klein, he suggested that by adding an extra dimension to Einstein's general theory of relativity, he discovered that electromagnetism came out. So you had gravity and electromagnetism coming from the same theory when previously they were disjoint if you added an extra dimension. So this has caught on since. And so to physicists, at least, it's not too outlandish, or to many of them, to ask for these extra dimensions. But if they exist, where are they? So one idea is that they are actually compactified, incredibly small distances that we can't perceive ordinarily. And this very simple slide will illustrate the point. So imagine you have a single dimension represented by this rod on the left-hand side. If you were to take a sufficiently powerful magnifying glass and you magnified it, you might be, if the extra dimension was there, you might be able to actually realize that this was a rod, not a pure line. And the extra dimension is that around the rod, as it were, around the circumference of the rod. It still sounds a bit odd because you'd expect that dimension to be within our own dimensions, but nevertheless, this is considered seriously within string theory, that somehow these extra dimensions are compactified within our own, within the material world. Now, even more probably difficult to grasp is this object here. And I have to confess, I really don't fully understand this. But anyway, this is called a Calabi-Yar shape, invented by mathematicians in the 20th century. And what it represents is the number of, each Calabi-Yar shape is a representation of how these 6 spatial dimensions can exist in a compactified way. And there are many, many, many combinations of them. And so there are many, many of these Calabi-Yar shapes. And at first, only a few were known. And so it was thought that each Calabi-Yar shape could be compared to what the various particles and forces are in our universe. And so we could establish which Calabi-Yar shape corresponded to our world, and therefore how these extra dimensions were compactified into our space. And how they are compactified is extremely important, because that determines in string theory what the masses are of each particle and what their interactions are. But it was found that actually there aren't just a few of these things. There are a crazy number of them. And in fact, you'll often hear an estimate of 10 to the power of 500. So that's 1 followed by 500 zeros. If you can think of that number, which is vast, of course, then there are an enormous number of these Calabi-Yar shapes, and there are far too many for us to analyze each one of them. Even automatically, it would take a vast supercomputer to do so.
So it's 10 to the 500, all of which are right, or one of which is right?
So it might, we would expect one of them to correspond to our universe, okay? But we don't know which one. And it's just such a ridiculous number. And in particular, not only would one of these shapes describe our universe as the expectation, it would also describe something called the vacuum energy. It's on the next slide. It's on the next slide, but 1. So hold that thought. Vacuum energy is really important for this talk. So just to summarize, one of these shapes, we don't know which one, corresponds to our universe if superstring theory is correct. And remember that each of these shapes describes the particular way in our universe that these extra dimensions are wrapped around each other. But there are a vast number of combinations, and we can't tell by looking at these shapes which one it is. So hold that thought in your head. I'm going to change tack slightly, but I'm going to come back to those ideas in a bit. There's only one slide on fine-tuning, but it's an important point. What fine-tuning refers to is that when we observe the universe, we find that if we were to tinker with certain things about the universe, such as the strength of the electromagnetic force or gravity, that the universe wouldn't be the way it is, and we wouldn't be able to exist. So it seems to be that the universe is fine-tuned for our existence. And I've got a few examples here. So I remember I talked about the vacuum energy. I'll tell you what that is later, but take my word for it. But if the vacuum energy were different to the value that we find it, there would either be no structure in the universe, because the universe would accelerate before structure could form, or the universe would have collapsed too soon after its formation for life to exist. And it turns out that this is a spectacular example of fine-tuning, which I'll talk about in a bit. Right. This is just a separate example. If the efficiency of nuclear fusion was less than 0.1% different to what it is, then only hydrogen would exist. And so therefore there would be no complex chemistry and therefore no life. And there is something called the Hoyle state, which was discovered, one of the first examples of fine-tuning, which is a technicality to do with the carbon-12 nucleus. There's energy states of the various atoms as there are, of the various electrons as there are in most atoms. And there's a third lowest energy state of the nucleus, and which is actually measured to be 7.656 mega electron volts. But if it were outside that range, if it were less than 7.3 or greater than 7.9, then insufficient carbon would exist in the universe, and that's fundamental to life. And these are, yes, they are technical, of course, but they are examples of how physicists have come to realize that our universe feels very finely fine-tuned for life. So when you come across this fine-tuning, you've really got 3 options. Either it's an amazing fluke and there's only one universe, or there is a providential God who deliberately created the universe so that we exist, and some people do believe that. Or the other alternative, the alternative that I'm proposing in this presentation, is that there is a vast ensemble of other universes. And of course, we only find ourselves in the universe that is fine-tuned for life, because if it wasn't, we wouldn't be here to talk about it. So that's the other reason, if you like, which is connected to string theory, as to why there might be multiple universes. Requires some thought, though. So now we're in part 2 of the talk. And this is about the Big Bang. And you may remember that last year I talked about the Big Bang. And in some senses, this talk is the companion talk to that talk, because that was all about what happened after the Big Bang. And this talk is really about what happened in some sense before the Big Bang, and is continuing today to create these multiverses. So I want to go over the Big Bang there because it's important context. So it was discovered just over 100 years ago, 101 years ago, by Edwin Hubble, with the support and background were building on the work of Vesto Slipher, who measured redshifts, and also Henrietta Leavitt, who discovered a technique for measuring the distances to distant galaxies, that the universe is expanding. And so when astronomers look at distant galaxies, if they can measure, and in most cases they can, the distance to the galaxy, which is quite difficult, but also the velocity, the speed at which those galaxies are moving, which is relatively straightforward using spectroscopy, then overall they discover that the galaxies are flying apart from each other. There are close exceptions because gravity overwhelms that expansion for very close, but broadly speaking, across the vast majority of the universe appears to be expanding. This does not mean, by the way, that we occupy a special place in the universe, but simply any location would see the universe expanding from that point of view. And that observation, if you were to play those galaxies, I'll stop it because it's getting a bit much. If you were to play that tape backwards, you would find that all the galaxies would be on top of each other. So the idea of the Big Bang Theory is that the universe began with a hot heap of particles. As it cooled and expanded, ultimately produced all the structure that we see in the universe. So at first, as represented on the far left-hand side, this explosion, which is a bit misleading because it implies that the Big Bang occurred at a single location in space, and that's not true. The scientific understanding of the Big Bang Theory is that it occurred everywhere throughout all of space. But for the purpose of a diagram, this makes it more straightforward to show it as an explosion, even though it is misleading. That hot heap of particles was so hot that the electrons, which did exist after a very, very short period of time, 10 to the minus 35 seconds or something, those electrons weren't bound to the nuclei, but the nuclei of the very first elements, hydrogen, helium, and lithium, some lithium, were formed very early on. And then as the universe cooled, those electrons combined with those nuclei at that line called recombination after 380,000 years. And that's when light passed through, was no longer scattered by the electrons and passed freely throughout the universe. And then, as per my lecture last year, gravity created the structure from the Dark Ages through to the present day on the right-hand side, after 13.8 billion years, where we find ourselves today, surrounded by the structure that we do. And the Big Bang Theory is tremendously successful at producing what we see today. There are some fine elements of galaxy formation that are still work in progress, but cosmologists, broadly speaking, are very satisfied with the Big Bang Theory. But the Big Bang Theory does not explain the bang itself. It's not a theory of the bang, it's a theory of what happened after the bang. It doesn't explain how the bang occurred, it doesn't explain what banged, and it doesn't explain the expansion of the universe. All of those things are inputs to the theory, not explained by it. However, in 1998, it was discovered that the universe is not just expanding, but accelerating faster and faster. And so it's not quite as alarming as depicted there, but that is meant to show you as in a rather alarming fashion, because I want to illustrate that the universe is expanding ever more rapidly. And this was completely shocking. The proponents who discovered this rightly won the Nobel Prize, because it was always expected that the gravity of the material in the universe, the galaxies, would hold back, would slow down over time. Not necessarily that it would collapse in on itself, but if it would slow down over time. And so the idea that it's accelerating was really shocking. And so the explanation is that it is not the galaxies that are causing this gravity, this acceleration, but something called the vacuum energy, the energy of free space. So you might think that the free space, the vacuum contains nothing. And in the classical view, before quantum mechanics of the 20th century, that would be the right answer. But quantum mechanics and later quantum field theory have shown us that there is no such thing as nothing. But there are such things called quantum fluctuations in empty space. And that means that particles, or virtual particles, are borrowing energy from the vacuum and popping into existence, and then giving that energy back and popping back into the vacuum. And that gives the vacuum an energy. And so that is what is causing the acceleration of the universe, and is what is referred to as dark energy. But the word dark just means I don't understand. We don't understand dark energy very well. So this slide is telling you the value in natural units, but natural units is a particular way of expressing values in cosmology and general relativity, which I won't go into. But the value of it, the take-home message is that the value is absolutely tiny. I mean, this is 10 to the minus, this is 1.39, 10 to the minus 122. So if you write this out correctly as a decimal, in full rather, it would be 0 point, and there'd be 121 zeros, and then it would be 139. So the message is this is really tiny. And in fact, modern physics cannot calculate this value. According to some theories of modern physics, some calculations of the vacuum energy, we get an answer that's 121 orders of magnitude more than this value. It's the worst prediction in all of physics. So anyway, hold that thought. It's quite important. So there are two, back to the Big Bang. Hold that thought in your mind as vacuum energy, this value. I'll come back to it. It's important. So anyway, back to the Big Bang. There are two problems with the Big Bang. And the reason for telling you this is that there is a solution to them called inflation. First is, when we look at that initial light, that light that I showed you several slides back, which is, sorry, that recombination light here at 380,000 years from the beginning, we find that that radiation appears almost exactly the same intensity all over the sky, to an incredible precision of 1 part in 100,000. And the problem is that, how can that possibly be? And I'll go into that next slide. And the next problem is, why is the universe so flat? So we can talk of the universe having a geometry, and I don't mean flat as in a flat piece of paper. What I mean is that if you were to draw an enormous triangle in space, the angles would add up to 180 degrees. But you can have open universes where the angles add up to less than 180 degrees, and you can have closed universes where they are like a sphere, where they add up to more than 180 degrees. So those are two questions. I'll go over those very briefly. So the horizon problem states, if we measure the intensity of this cosmic microwave background radiation, this recombination radiation that I mentioned earlier, in one part of the sky, and we measure it in the opposite part of the sky, they are exactly the same temperature to 1 part in 100,000. How can that be? Because when they were first, when the universe was only 380,000 years old, there wouldn't have been enough time for energy to communicate, to smooth out the temperature. You need signals to smooth out the temperature of a finite body. And it turns out that light would have to move at about 100 times faster than it does for that to happen. So there's a problem there. Why is the universe incredibly smooth when it shouldn't be? Those two regions shouldn't have two regions opposite to each other in the sky would not have had enough time to communicate that they have the same temperature. So why do they? And the other one is the flatness problem. So as I mentioned, there are at least three in the simplest models, there are three possibilities for the curvature of space. Either it has a flat geometry, or it has an open geometry like a saddle, or it has a closed geometry. And it turns out that we have measured the universe's curvature to be 1 to within the accuracy that we can measure it. So I think it's about 3 significant figures. So it turns out it's extremely flat. And the Big Bang Theory can't explain that. And the reason why it's a mystery is that if it wasn't precisely flat at the time the Big Bang started, to an extraordinary precision, this is another example of fine tuning. If it wasn't flat to an accuracy of 15 decimal places, if it wasn't exactly 1 to an accuracy of 15 decimal places, so 16 significant figures, 1 second after the Big Bang, it would be hugely different today, because it diverges very, very quickly from 1 if it's not 1. And that's illustrated by the graph on the left, which is saying the time on the x-axis and omega on the y-axis. If it wasn't precisely 1 over time, it would diverge from 1 very quickly. And also pictorially by this pencil, if being on its tip, if a pencil is on its tip is represented to be omega to 1, the slightest perturbation, the slightest touch will send that pencil tipping over. So that's another way of thinking about it. So it's phenomenally unlikely that it would be 1 unless there is some physical mechanism. And that mechanism is proposed to be inflation. This was proposed by Alun Guth, a particle physicist, in 1979. And the idea is that very early on in the universe, predicted by some theories of grand unified theories, there would have been a patch of material which had what is called a scalar field. That is, a field that has a positive value of energy at each point. And that expanded exponentially. So you can think about, and it expanded to at a vast rate to completely account for the visible universe in a very, very short period of time. So the idea is this patch of very special material, and we can't reproduce it with our current technology, a size only 10 to the minus 28 centimeters across, which is about the billionth the size of a proton, underwent an incredible exponential expansion, doubling in size every 10 to the minus 38 of a second. And it therefore expanded by a figure of at least 10 to the power of 28. So that tiny patch of material ended up being the size of a marble, which doesn't sound very impressive. But what is more impressive is that it then coasted and became larger than the size of the visible universe that we see today. So the exponential expansion, amusingly, is a bit like when you were conceived. Okay, so when you were conceived, your mother's egg was fertilized, and that egg then split into 2 within 24 hours, and then each of those cells split into 2 the following day, and then they split again, and so you keep getting this doubling until about 3 weeks. Till you're about 3 weeks old, and then it tailed off. And this is quite similar to the universe. It doubled in size using inflation, if this inflation idea is correct, until it got to about the size of a marble, and then it coasted. Now, if you had continued, just to say that if you had continued doubling in size all the way through the 9 months, then you would have ended up larger than the visible universe, and your mother would certainly have complained. So that is just to give you an idea of what exponential expansion is like. So in this diagram, you have a tiny patch of this material expanding exponentially, and that's illustrated by the dotted line labeled inflationary expansion, either side, top and bottom of the blue circles. The blue circles illustrate over time the size of the universe, and the orange represent how fast light has traveled during that expansion. That might confuse you a bit, because you might think, well, nothing can travel faster than light, but that's only true in special relativity. Space can expand in general relativity, and it is allowed that space can expand faster than light. So today we find ourselves at position 5, and that uniform region today that we see is the size of the visible universe, is the size of the entire universe, which can be much larger than the visible universe that we see today, but still our universe. Okay, this is just a few more graphs. So there's a graph here of the exponential expansion, and on the right hand side we see why inflation results in a very flat universe, because any irregularities would have been swamped by the exponential expansion. And it also solves the horizon problem, because the original patch of material would have been easily small enough for signals to have made its temperature almost exactly the same, and therefore when it's blown up and we see it all around us, we find therefore naturally that the temperature in different regions of the sky is exactly the same, to 1 part in 100,000. And so this is the light that we see today, the cosmic microwave background. As I say, the variations being very, very slight. What's interesting about it is that although the color in this diagram illustrates the temperature variations, But these started off as quantum fluctuations, beginning in that tiny patch that inflated that I told you about. And that then became, those quantum fluctuations then become, tiny though they were, all the structure that we see around us. So I've talked about inflation and why inflation is a compelling idea, because it solves the problems of the Big Bang Theory. It solves the horizon problem. It solves the flatness problem. It also solves something called the relics problem, which is the monopole problem. We expect to see lots of monopoles, which are single north or south poles, but we don't see them. They're expected from grand unified theories, but we don't see them because they have been stretched to vast distances apart from each other due to the inflation. Anyway, so what I've described so far is superstring theory, fine-tuning, and how inflation and how inflation solves the problems of the Big Bang. And when you marry inflation to superstring theory, you get this compelling idea that there might be millions of universes, perhaps an infinite number, and I'll try and explain why now. So the idea is that inflation stops when that scalar field that I mentioned decays. Okay. And when that decays is not predictable, it could happen at any place and any time. So you have this patch of material expanding exponentially, then at some point it stops. But when and where is not known. It is not known beforehand. So it's a bit like radioactive decay. You can't predict it precisely. So the idea is that there isn't just this universe, that the inflating region is somehow all of leads to the creation of billions and billions of universes. And when the decay, when that inflation field decays at a particular time and location, it dumps all of that surplus energy into the surrounding space, which becomes all the particles and all the galaxies that we have. And it also explains why all of that is then expanding. So we as observers are sitting inside a universe that was the result of the decay of that scalar field, and that it happens again and again and again. This inflating region keeps going forever. Once it starts, it keeps going forever, and that's called eternal inflation. And this is a very simplistic diagram, which I want to illustrate. So so the blue sweeping lines are the inflating patch moving, inflating exponentially. We've got time moving from top to bottom, and we've got this dotted line which represents now. Okay, so I'm going to run the animation. It's very simple because I created it. So we're going to find that dotted line moving down, and as it moves down, we're going to see little universes being created due to the decay of the scalar field within that blue expanding line. Okay, so there's one, there's another, there's another, there's another, there's another. And we live, I'll run it again because I've spent a lot of time doing this, so I might as well show you again. So here we go. These universes coming out of this decaying, inflating region. Now, what I'm not showing is that actually the region, the space between those white blobs, let's do it again, why not, is actually expanding exponentially itself, and I can't show that. So these bubbles aren't remaining at a constant speed from each other. They're being torn apart from each other because the remaining inflating space is still expanding exponentially. And that expansion, this expansion you see here with these curved sweeping blue lines, occurs forever. It didn't necessarily have always occurred, but it started at some point.
They kept apart from each other because they travel away from each other faster than light. But
yes, much faster.
But inside, then they can still see everything else that's in.
Yes. So we are in one of those white circles.
Which is basically, I don't know if it's the right terminology, it's the same space. It's just, you want to call it that.
Yeah, it's really difficult.
Too fast.
Yes, exactly. Yeah, so I'm not in.
It's not like this.
Yeah, so that's very interesting actually. So I've read, and I struggle with this, is that from this perspective, each of those spheres is finite. But according to general relativity, when you go in one, it can be infinite, which is really, really odd. And it's to do with the idea of the concept of simultaneity, which is not intuitive in general relativity, and that you can, what is infinite space in one for one observer can be infinite time for another. This is really tricky, but nevertheless, the idea is that each of these, let's run it again.
Each of the spheres are expanding.
Yes, each one is expanding, and that's what I've shown here. So each of these is a Big Bang, and each observer inside those sees it as a Big Bang, but there are an infinite number of them, and they're constantly being created. Right, it's good. I hope that's okay. So I try to, this is a diagram, this is not my diagram, but this is another way of thinking about it, is that you have this false vacuum is the scalar field that I mentioned, and that it starts off at the top, this is top going down, you end up with this hierarchy. So at the next level, you still get this false vacuum, but then the middle one spontaneously decays into a Big Bang. And then on the left-hand side, you have the same thing on the right-hand side. Each of the false vacuums may or may not decay to a new universe. So you get all this hierarchy of new universes being created all the time. Now, the next important point is that each of these new universes is potentially a different Calabu-Yar shape, a different way in which those extra dimensions are wrapped up with each other. And therefore, there is a different set of particles, a different set of charge-carrying particles, and the forces of nature are different. And we find ourselves in the one that is fine-tuned for life because we would not be alive otherwise to talk about it. But most of the universes are dead because they cannot, they either collapse in on themselves because the vacuum energy is also different in each of them. And if the vacuum energy is negative, it will collapse in on itself. So you have all these universes. So this is a more of a pictorial way of describing what's happening. This is actually taken from Brian Greene's TED talk. I must acknowledge him in this because a lot of the ideas come from Brian Greene's The Hidden Reality, and also Max Tegmark's book on the mathematical universe. So the idea, you have all these Big Bangs going off. Each of them is a separate universe. Each of them has a different Calabu-Yar shape corresponding to it. Therefore, each one of them has different strengths of the different forces and different particles, therefore, and the numbers that you see here are different values. Sorry, it's a bit much, isn't it? Different values of the vacuum energy. And the reason why, therefore, is the suggestion that we can't calculate this vacuum energy is because there's no way of calculating it. It's a bit like calculating, a bit like asking, why is the distance of from fundamental physics, why is the Earth at a particular distance from the sun? It could be at any distance, and we see planets that are at different distances from their host stars. But we live on this one because it happens to be right for us. Now, many physicists don't like this idea. They want to be able to calculate the properties of the universe from first principles. They want the theory of everything to be able to explain the forces of nature and the way that our universe is. But string theory is suggesting that combined with inflation is suggesting that there are actually a vast ensemble of other universes that really do exist now. And you can't answer, therefore, why you can't calculate the vacuum energy. It's just that's the energy that our universe has. I think that's clear. Here's a pictorial representation of the multiple universes. I quite like this. It's quite like bubble bath, sort of bubble bath universe, very pretty. Now, this is the other interesting thing, is that each universe is its own reality. And according to eternal inflation, there are an infinite number of them. I have a problem with this because we know that eternal inflation must have begun at some point, but it could have started an arbitrarily long time ago. And what we're saying here is that the Big Bang is not the beginning of time. Okay, the multiverse has a different concept of time that goes back much earlier. But anyway, it started at some point, and that each one has its own reality. And if there are an infinite number of them, because there are only a finite combination of them, 10 to the 500 Calabu-Yar shapes is a vast number, but it's not infinite. That means that every one of them, each has a version of reality. And that means that one of them, this lecture is carrying on in this exact same lecture is carrying on in one of these bubble universes, okay? And an infinite number of them as well. And also there's an infinite number of slight variations. So there will be a version of this lecture where Maria is in some universe dressed as Harry Potter. There'll be another universe where you get everything you want for Christmas or your heart's desire. You know, so that every kind of reality is possible. So your doppelganger, some incredible distance away, will exist in some alternative universe. And so this is one of the extraordinary consequences of the multiverse theory. So to wrap up, is there any evidence? Could we ever think of an evidence that there might be for a multiverse? So I should unfortunately disappoint you that there is no evidence currently, and there may never be any evidence, I should say, if we're honest about it. But it is possible, although unlikely, that bubble universes can intersect. Because if they form close enough, and they have to form extremely close to each other, then they could expand into each other before the exponential expansion carries them away. And if that happened in our universe after 400,000 years, after 380,000 years, when this light occurred, then we might be able to see that in the imprint. We might be able to see the intersection of another universe in our universe from the cosmic microwave background. And there have been one or two claims, but they haven't stood up to scrutiny. So I have to disappoint you and say that there is currently no evidence, but it's not completely outrageous to think that there might be. And to finish, what I thought I would end on is by letting you know what cosmologists think of the multiverse. So Martin Rees, who is the Astronomer Royal, an eminent astrophysicist, and he's a supporter of this theory, but only to the extent that he would bet his dog's life that the multiverse exists. Now, Andre Linde, who's one of the founders of inflationary theory with Alun Guth, he's much more confident. He said he would bet his life that the multiverse theory is true. And then Steven Weinberg at a conference got up and he's talked about, he was one of the first people to talk about fine tuning. He's also won the Nobel Prize for unifying the electromagnetic and weak forces. He stood up and said he was so confident in the multiverse theory that he would bet Martin Rees's dog and Andre Linde's life that the multiverse exists. Thank you very much.